Every year, hundreds of scientists and tons of supplies and equipment arrive in Antarctica from around the world. Why is there this huge investment in men and materials in the bleak continent at the bottom of the world? There are a number of answers. For the scientists themselves, though, it's simple. The quest for knowledge.
Release! Release!
Antarctic science is very exciting at the moment, for it's just beginning to show how the remote continent fits into our world, and how we, mankind, are affected by it. Take climate. Since the earliest days of man in the Antarctic, meteorology has been one of the routine chores. With 25 years of continuous data, we now have a fairly complete picture of just how extreme the climate really is. Antarctica is the coldest continent. The world record low temperature was recorded here at Russia's Vostok station. It was a mind-numbing 88 degrees Celsius below freezing point. Surprisingly, in spite of the extreme cold and the 6-month-long winter night, the sun shines at the South Pole for about as many hours each year as it does at the equator. But there isn't much heat in it. The sun stays low on the horizon, even in midsummer, and the brightness of the ice reflects a lot of the heat away. Another surprise is that it doesn't snow as much as you'd expect, except around the coast. Almost no snow falls on the high central plateau. In fact, less moisture falls here each year than in the Sahara Desert, making Antarctica overall the driest continent. But the little that does fall can't melt, so it accumulates bit by bit. Over millions of years, it's compacted into a vast sheet of ice, covering virtually the whole continent. Only occasionally do mountaintops push their way through from far below. Mostly, though, the ice sheet offers an unbroken surface to the wind.
Might be better to pick this sign up. Pull it. Should sail otherwise.
Gravity pulls the cold, heavy air down the long, gentle slopes of the plateau towards the coast.
I think you've got to turn it in upside down.
For somebody caught out in the open, every extra mile an hour of wind speed is felt as at least another degree drop in temperature.
Turn it over.
And wind speeds average over 40 miles an hour, often gusting well into the hundreds. Antarctica is by far the windiest continent. Today's sophisticated equipment makes it easy for us to see the working of this great weather factory. Daily satellite photographs show how the rotation of the Earth causes the winds pouring outward from the pole to twist into a ring of spiraling cyclones. They make the oceans around Antarctica into the zone of the strongest sustained winds anywhere on Earth. Clearly, then, Antarctica affects the southern hemisphere. But to see how it affects the whole world, we have to look to its ice. It's almost impossible to grasp just how much ice there is. For example, altogether, it's estimated to weigh some 20,000 trillion tons. That's 9/10 of all the world's ice. Or try this. If it all melted, sea levels around the world would rise by about 240 feet. That's enough to drown most of our major cities and over half the areas where we produce our staple foods. Look at it another way. On land, the ice sheet is on average over a mile thick, and in area, it's bigger than the United States of America. But add the winter sea ice, and this more than doubles. That means there's a reservoir of cold equivalent in area to the whole of the North American continent, plus Greenland and Iceland, both East and West Europe, and a chunk of the Middle East as well. It's not surprising, then, that studying the ice is a whole science in itself. For the glaciologists, probably the simplest and yet also the most difficult question is, how old? We think about 15 million years. That may seem like a long time, but actually it's less than half of 1% of Earth's total history. In some ways, we can get very accurate answers. The different quality of summer and winter snowfalls allows us to date the recent layers with considerable precision. The scientists once sent a sample from the year that Jesus was born to the Pope in Rome. But some questions aren't easy to answer because we haven't got enough long-term data. It's arguable whether the ice sheet is growing or getting smaller. But we're beginning to see what role it plays in the global climate system. It's the last really large ice sheet left from the ice ages, and it's on the move. Slowly but steadily, huge ice streams pour outward from the central plateau. In West Antarctica, these ice streams are held back by two huge plugs, the ice shelves. The larger, the Ross Ice Shelf, is the size of France. George Denton from the University of Maine has spent 15 seasons in the Antarctic. He sees the ice shelves as the key to understanding the Ice Age world that we live in.
The fundamental scientific problem that we're attacking is the cause of ice ages. And the particular problem within this overall search is to discover why large ice sheets come and go in the past.
Look back 10,000 years, about the duration of man as a civilized being. World temperature has varied in that time, but seen against the span of 1 million or so years, those variations become lost in the latest warm peak among the extreme swings of temperature that we call the ice ages. Many theories have been tried to account for the swings. One of the most promising calculates the changes in the amount of heat received from the sun in parts of the northern hemisphere as a result of slight irregularities in the Earth's orbit, and in the way its axis of rotation rolls and wobbles. But each irregularity varies the warmth of the Earth differently, and sometimes warm or cool points coincide. At others, they cancel each other out. So calculating the combined effect calls for skillful judgment and mathematics, but it produces a graph that shows how the temperature should, in theory, have varied. New techniques allow us to work out accurately how temperatures actually have changed. Theory and evidence show remarkably similar patterns. For the scientists, though, there's a gap between a probable cause and the known effect, and it's as part of a possible link between them that George Denton sees the ice shelves. Suppose the Earth's movements did cause a slight warming in the northern hemisphere.
One of the exciting things that we've discovered is that regional climatic changes in portions of the northern hemisphere have a widespread global effect. A slight climatic warming causes melting of the northern hemisphere glaciers. Water pours into the sea, and the worldwide sea level rises. In Antarctica, this causes the ice shelves to lift off their pinning points. This has the effect of loosening a cork in a bottle. It allows more ice to flow seaward, and this occurs until a new equilibrium is achieved. This is exciting to us because it unifies the entire ice sheet system of the globe.
So sea level transmits climate messages between ice sheets and ice shelves at different ends of the Earth. And it helps to fill the gap in our understanding of the comings and goings of the ice ages. For changes in sea level do more than simply transmit messages.
Under certain circumstances, particularly during warm interglacial climates, this cork can conceivably be removed entirely by being melted away. And under such circumstances, the marine West Antarctic ice sheet could conceivably collapse entirely.
If that part of Antarctica's ice sheet were to collapse, sea levels would rise by some 20 feet, about the height of this tug. Besides putting every port in the world out of action, the new areas of cold water would drastically alter local climates in many parts of the world. We think that this is what happened at the peak of the last warm spell, triggering the start of the following cold spell. And interestingly, world temperature now is very close to what it was then. George Denton's work, then, shows how the world's climate has to be treated as one single system, particularly how a modest change in the north can have profound consequences in Antarctica. But how about the other way around? How does the ice sheet, the huge reservoir of cold, affect the rest of the world? It's when it changes that we can most easily see the answer.
Forward, easy forward, steady, ease down, ease down, on deck.
There's no better place to see how the ice sheet changes than in the dry valleys. Here flows Antarctica's only river, the Onyx. It flows only in summer, for it's fed by meltwater from the glaciers, and in turn, it feeds an inland lake. Because the system is enclosed, river and lake become a simple measure of changing climate. The warmer the summer, the more water in the river, and the higher the level of the lake. On the sides of the lake, there are fossilized beaches or shorelines, proof that at times in the past, warmer climates have put more water into the lake, and so there's been even less ice around the valleys. But the valleys themselves are a classic demonstration of not less ice than now, but more, for their curved shape was scooped out by enormous glaciers which have long since vanished. They're just the kind of thing we find in the northern hemisphere, where the Arctic ice sheets advanced and retreated over land. Since Antarctica is surrounded by sea, how do changes to its ice sheet affect lands far away? Michael Selby is Professor of Earth Sciences at Waikato University.
Most of the evidence we have for climatic change has come from the northern hemisphere, where the fluctuations of the ice sheets have been regarded as the best evidence of all. But we now realize that Antarctica has also controlled climate because it pushes ice into the Southern Ocean as icebergs, cools down the surrounding seas, and creates cold currents.
So again, it's the sea which sends the climate message. Antarctica creates cold currents, and these spread north. Due to the rotation of the Earth and the shape of the seabed, they pass up the western sides of the southern continents. This is the southwest African coast. The prevailing winds here come off the sea, but the cold water they pass across makes them drop their moisture. By the time the air reaches the land, it's very dry.
So that the Benguela current, which is the cold Antarctic water upwelling off the southwest African coast, makes the climate of southern Africa very dry. That is, it creates the Namib Desert.
The Namib Desert, created by Antarctica 3,000 miles away. Compared with other deserts, it's old and harsh. Old because it was created when Antarctica iced over 15 million years ago. And harsh because the Benguela Current has kept it unusually dry. How do we know?
The best evidence we have of all comes from a site called Narrabeb, where there was a very small lake, which probably resulted just from a single storm, perhaps a long thunderstorm, and sediment in the form of calcium carbonate precipitated out of that lake, and we've collected samples from it. We've dated those samples in this laboratory, and the date is 200,000 years. Now, if the climate had become wetter in that 200,000 years, those carbonates would have been washed away. In fact, the core of the desert, we believe, has not become wetter, perhaps over the last few million years. This is unusual, because most deserts had a fluctuating climate between the wet and a dry condition.
But there is some evidence of fluctuating climate around the edges of the Namib. Inland, it joins on to the high Kalahari Desert. Like most deserts, it does sometimes rain in the Kalahari, and when it does, the water flows down into the Namib, creating riverbeds and cutting terraces through the ground.
And on the surface of those terraces, there are old soils which have got root casts in them. Those root casts are the sort of casts which today are still being formed in the wetter parts of some deserts. Those root casts are made of calcium carbonate, again which can be dated. So there's a combination of the two pieces of evidence. The river terraces themselves, which could only have been formed by a large river coming from the interior, and the vegetation that was growing on them.
But during the ice ages, the centre of the Namib didn't change much. It didn't respond to changes in the amount of ice in the Antarctic. But remember, these valleys were once full of ice, and when they were, Antarctica caused profound effects elsewhere.
When Antarctica is pushing more ice into the ocean, the Benguela Current gets larger and pushes further north right up into the Gulf of Guinea. As a result, the precipitation along the West African coast declines dramatically, and the source of rivers like the Niger becomes drier, and therefore the rivers themselves are much less in volume. The Niger evidence is perhaps best shown in satellite photographs, where we can see that the Niger River has at various times dried up completely, and active sand dunes were blown across its bed. When the Benguela Current declines again to a lesser volume, rainfall increases, the rivers start flowing in their old channels. Often they're ponded by the sand dunes of the previous dry period, so that we see inland lakes and deltas formed, and then eventually they break through the sand dunes and re-establish themselves in their present courses.
So how the Niger River flows is governed by how much ice there is in the Antarctic, and the Niger is north of the equator. 8,000 years ago, the world was warmer, so the Benguela was smaller and West Africa wetter. Rivers flowed, lakes grew, the Sahara Desert retreated, and the tropical Congo rainforest advanced. What happened at the peak of the last cold spell?
The very arid influences of the Sahara, of course, were extending further south. But at the same time, the very dry conditions in the Namib, which were extended further north by the Benguela Current, meant that the two deserts almost met in the area which is now the Congo rainforest. The rainforest disappeared, or almost disappeared. And in fact, sand dunes crossed what is now the bed of the Congo River. The river itself, of course, had dried up.
So where now there is luxuriant jungle, only 20,000 years ago, it must have looked more like this. And the Antarctic ice sheet was the trigger. This is just one example of Antarctica's influence on the rest of the world, and on us. Remember that lake, where it hasn't rained for so long? Lying about on the surface are the tools of Stone Age men, relics from a race of hunters who vanished as changing climate caused the game to move elsewhere. They, of course, didn't know why, and they couldn't have done anything about it if they had known. We, modern man, are coming to understand it, and perhaps even to bring it about. Think how close we are to the temperature when the West Antarctic ice sheet is thought to have collapsed before. George Denton.
The fact that mankind is introducing CO2 into the atmosphere has led some meteorologists to suggest that within the next 75 years that the world's atmosphere will warm.
The greenhouse effect, atmospheric warming caused by increasing levels of carbon dioxide in the air, is a complicated issue. Some scientists feel that if it is operating, it is being cancelled out by other cooling factors. But a recent paper strongly argues that the warming trend will soon dominate and that temperatures will rise. Industrial man has almost doubled the amount of carbon dioxide in the air over the last 100 years. The paper reasons that however we fuel our expanding societies, this is likely to double again in even less time, driving temperatures further up. It goes on to describe what we're doing as the most fascinating global geophysical experiment that man will ever conduct. Put everything we've looked at together. A small temperature change in the north has dramatic effects in the south. In turn, those can create deserts and destroy jungles. They could even trigger the next cold ice age. We, mankind, could be accelerating these changes with profound consequences to our world within the lifetime of our children.